Good morning, students. Can you all see my screen?
Yes, miss.
Okay, so last session we discussed about a brief introduction about R, how to store your objects and what are the data types, and how to import data as an Excel file to R. So today we are going to discuss about simple linear regression model, how to obtain your outputs using R. So let's say you have a data set, you have X variable and you have a Y variable. For an example, let's say X is weight and Y variable is height. So if you are no, we'll take it in the other way around. Let's say X is height and let's say your Y variable is weight. I'm just writing the names of the variables. Right, X is height and Y is weight. And in this case, if you want to fit a regression line using X and Y, we can do it in R. For an example, first what you have to do is you have to store the data set for this X and Y variables. So if I take X variable, now my X variable is height. So let me take some values for height. Let's let's imagine height is recorded in centimeters. So I'm going to store some values for height. So I have stored these values for X, for height, and if I take weight values, I can store another set of values for weight. Let's say it's 63 and 81, 56, 91, 47, 57, 76, 72, 62, and 48. So now we have stored our data set. We have X and Y. So one thing when you're going to fit your regression line that you can do is you can check whether there is a linear relationship between X and Y, whether it's okay to fit a regression line between these two variables. That can be done by observing the scatter plot. So to obtain the scatter plot, this most simplest function is in R, that is plot. So you can use the function plot, and last session also we discussed this function. So inside the brackets, you have to give your X variable and Y variable. So I'll give X and Y, and when you enter, you will see your X variable and Y variable. And here in this case, you can clearly see there is a linear relationship between X and Y. So it's okay to fit a regression line between X and Y. So first you can examine that using X and Y. So this is the most simplest function in order to plot X and Y. So using the same function, what you can do is, now if you look at this plot, we cannot see the title of the plot. So using the same function, if we want, we can just add some other things to this function. So before adding that, I'll tell you how to fit the regression line. Now, after observing the scatter plot, we can again check if you want the correlation coefficient between X and Y. To do that, we are using the function co in R. So you have to type co, and within brackets, you have to give your two variables, X and Y. So in this case, we can see there is a strong positive linear correlation between X and Y, that is 0.977. So we can go for a regression model. So in this case, when we are going to fit a regression model, the first thing that we have to do is we have to give a name to our regression model. For an example, let's say it's fit 1. You can give any name as you like. And in R, what we are using is the function that we are using to fit a regression line is LM. So in this LM function, what you have to do is now you can fit your regression model. And in this case, first you have to give your Y variable when you're using this LM function and this mark and your X variable. And then if you just type your the name that you gave to your linear model, in this case it's fit 1, so you will see an output like this. You can get the same output if you write print and within brackets if you gave the name as fit 1. So you will get the same output. So you can use whatever the output you like. Now, in this case, if you observe the output, you can see it gives you the coefficients of the regression line that they have fitted. Okay, so in this case, you can see the coefficient is, the intercept is equal to minus 38.4551. And the slope is 0.6746. So likewise, you will see the intercept value and the slope value when you fit the regression model. Okay, so that is in this case, beta naught is minus 38.45 and beta 1 value is 0.6746. So that is the basic form that you can obtain the results of your linear regression model for the simple linear regression. And if you want to obtain more detail regarding your model that you fitted, what we have to do is we have to use the function summary. So we use summary, and within brackets, you can give the name of your regression model that you fitted. So in our case, it's fit 1. So when you press enter, you will see this output. So this gives you a summary, a full summary of your regression model. Okay, so if you just check, now they are saying this is the regression model between X and Y. And here they are talking about the residuals first. You can see the minimum value of the residuals, first quartile, third quartile, median, maximum value, and then you have the coefficients here. So if you look at the intercept, that is beta naught, you have the estimated value. Beta naught hat is 38.455. And then here, the next one is the standard error. So you have the standard error here, and you have the t value. And then you have the probability where the t value is greater than your table value. So that probability is also given. And if you look at this output, you can see some stars here. And in the next line, you have your variable x, and the coefficient is given. So x coefficient means the slope, beta 1. So the beta 1 hat value is 0.6746. And you have the standard error and the t value and the probability. And again, you have some stars. So if you observe the next line, it says the significance codes. And you can see if you have 3 stars it's 0. And if you have 2 stars, it's 0.001. If you have 1 star, it's 0.01. If you have a dot, 0.05. Likewise. So we know when we do hypothesis testing, we are taking the significance level as 0.05. So that is what they are talking about here. Now, in this case, if you look at the intercept, now the estimate that they have got for intercept, that is the beta naught hat minus 38.45509. This value is significant. This value is significant under 0 significance level, right? Sorry, it has 2 stars, so it's 0.001. So this estimate is significant under 0.001 level of significance. And if you look at this one, here beta 1 hat, it has 3 stars, so it's significant under 0 level of significance. So that's why the significance level is the one that they have given here using codes. So in this case, if you look at, if you observe your output furthermore, you will see the residual standard error is there, the associated degrees of freedom, and R square value is there, the adjusted R square value is there. So when it comes to simple linear regression, we are actually interested about the R square value. And then we have the F statistic here. And here the degrees of freedom and the p-value, everything is here. If you can remember when we were discussing about the simple linear regression, and there we did, when we wanted to check the hypothesis for beta naught, and when we wanted to check the hypothesis for beta 1, and when we want to obtain confidence intervals, in that case, we wanted this t-test statistic, right? And then this standard errors we wanted. So here from this output, you can easily obtain them in order to do the hypothesis testings individually for these coefficients. And we will discuss examples when we discuss in sample questions, right? And in this case, you can use the standard error values and you can use these t values to do those calculations. So if, and then in simple linear regression, we also obtain the Anova table. So it's possible using R as well. So the function is Anova, and within brackets, you have to give the name of your fitted regression model. In my case, it's fit1. So here you can see when I enter, you can see your response variable is y. And when it comes to x, that is your predictor variable or the independent variable, and the degrees of freedom is 1. So we know in simple linear regression, when it comes to the Anova table, since we have only one x variable, the degrees of freedom is always equal to 1. And then we have the sum of squares. So that is sum of squares, which is coming from the regressor, that is SSR. And then we have the mean sum of squares, and then we have the F value. And then when it comes to the residuals, here we have the degrees of freedom and the error sum of squares, and we have the error mean square values. And then we using these two, they have calculated this F value and its probability. In this case, you can see this F value is significant under 0 significance level. That is, we can conclude our model is significant because here we are testing for beta 1 and the beta 1 coefficient is significant using, if you look at this output, because as we can see 3 stars here, it's significant under 0 level of significance, so that we can conclude there exists a beta 1 coefficient. So that is our model is significant. So in this case, actually, when you call a function Anova, you can see they are giving values only for the X variable and only for the residuals. So we can't see the total sum of squares. So what you have to do is, if you want to obtain this Anova table manually, you can just take all these information and you can add another row as the total, and you can just add these degrees of freedom, that is 8 plus 1, and the degrees of freedom for the total would be 9. And for the sum of squares, you can add these two values, right? And then for the mean square, we are not calculating for the total. So the total row also you can obtain using this information. So that's how we use simple linear regression in order to fit a simple linear regression model using R. Now, in this case, if you just, I told you the basic form to obtain the scatter plot is the plot function, which we used here. This is the function that we used. But in this function, we can modify this function by adding a title, and by adding a name to your x-axis, by adding a name to your y-axis, likewise. So to do that, what you have to do is, now when you get the output of your the scatter plot, now I will call this function again. You can see when we call this function, the dots of the graph, as in default, there is no color for the dots of this graph. So we can change everything. We can modify your output or the graphics that you are taking in, that you obtain from R, the way you want, right? So what you have to do is, we are going to use the same function plot, and if you want to give a color to these observations, if you want to plot these observations using a particular color, that can be done using the code call, that is the color. So inside this plot function, you have to just indicate what color you want to use to plot these observations. So I'll just keep it as blue, and then you can give a title. So last week also we discussed, in the last session also we discussed this one. So you can use the code main to give a title. So let's write height and weight regression as the title, and then we can give actually a name. We can name our x-axis and we can name our y-axis in the chart. So if you want to name your x-axis, you have to use the code as xlab, that is x label. So then equal, you have to give the name for your x-axis, and let's say it is weight in kilograms. Right, it is weight in kilograms. And then what you have to do is, then we can give the label for our y-axis using the function ylab. So that is, we can give ylab is equal to the name of the y-axis. Let's say let's say height in centimeters. So I'm just going to call this one. So you can see when I add these things, we have now when you observe your output, now you have a title for your plot, and when you have a when you look at your x-axis, you have again, you have a label for your x-axis and you have a label for your y-axis, and the observations, they have been plotted using blue color. So if you want to further modify this one, if you want to indicate the fitted regression line into our scatter plot and observe how it looks like, whether there are so many deviations with this true value and the fitted line. That also can be done. Right, so what we have to do there is, I'm going to use the same code and I'm going to add some more stuff to that same code. If we use this code abline, using code abline, we can do that. If you use abline and within brackets, what you have to do is we have to give the fitted regression line. So in that case, I'm going to give the fitted regression line, linear model. There we are going to give the X variable first and the Y variable. So then it will show your fitted line in the chart. And then what I'm going to do is, after this abline, I'm going to add these two codes as well. CEX, the sex code, and I'm going to fix this value to 1.3, and I'm going to use PCH as another code. I'm going to add this value, let's say as 16. Now let's see what will happen when we add this abline and these two new codes to the plot. So you can see when we get the output like this, now here, the things have been changed. Now we have, if you look at the output here, you have the observations are plotted using blue color, but the observations, they have been plotted using a circle, and the circle has been colored, right? And here what we have done is, when you use the same function and when you use this CEX code and PCH code, CEX code is the size of this observation that you are going to plot. So when you change this sex value as to 1.3, 1.5, you will see the size of the observation that you plot, that will change. And this PCH value is the character that you are going to use to plot this observation, whether that is a colored circle or whether that is a triangle. So you can just go to R and check what are the possible values that you can use to this PCH and CEX to change the output of your regression model. And in this case, so if you want to know anything in R, you can go to help and you will see here you have manuals in PDFs, and you can just click an introduction to R. So in that case, you will see, you will get, when you click this one, you will get all the information regarding all the functions that you can use in R. Okay. So that we can done, and we'll just have a look. We can do the same. Okay, I'm going to do another example regarding the simple linear regression. I'm going to use a built-in data set in R to do an example. In this case, if you look at the data sets in R, there's a data set called cars. You just use this data set cars, you just type cars, you will see there are some values. There is a data set called cars in R. So if I just type head and cars and enter, you will see only the first 6 values of this data set. So you can see there are 2 variables, speed and dist. Right, speed and dist, and we are going to fit a regression model using these 2 variables. So in this case, we can fit a model to predict or to forecast the distance of these cars using its speed. So in that case, we can take our y variable as dist and x variable as speed. So the first thing is to do to obtain the scatter plot. In that case, to obtain the scatter plot, we can use the function plot as I just explained, or else you can use this function, that is scatter dot smooth. You can use this function as well. And in that case, I'm going to I have to, when you are using this function scatter dot smooth, you have to give what is your x variable and what is your y variable inside the brackets. Now, when it comes to my x variable, that is coming from the built-in data set cars. And I'm going to take speed as my x variable. So what I have to do is I have to first write the name of the data set, and I have to use the dollar mark in order to say I'm using the variable from this data set cars, and then I have to write the name of the variable speed, comma, and then here I can write y variable is cars dollar mark dist. These two are the variables that I'm going to use to fit the regression model. And then in this case, I can give an let's say I'm going to give a title for this one. So let's say it's regression between say dist and speed. Right, and then what I have to do is after running this one, I have to call the function after using this function scatter.smooth, and after entering all these values to this function, after passing these variables, then I have to call the function again scatter plot. Sorry. Let me call this function again. And now I should obtain, yeah. Now you will see the scatter plot between regression, that is the scatter plot between distance and speed. So the difference between the scatter plot that you can obtain using the function plot and using this scatter.smooth is, if you look at this one, this is more precise because you can see the trend of your regression, whether it's having a linear relationship or non-linear relationship when you use this scatter.smooth function to obtain the graph. So you will see a graph like this. So that's okay. You can use this function or the function plot to fit the regression model. Whatever the function you can use, that's all right. So the next thing that we are going to do is we are going to check. Now, the two variables that we are going to use is the speed and the distribution distance. The two variables are coming from the data set cars. So what we can do is we can just check whether there are outliers in these two variables. That can be done using, if you observe, if you just observe the box plot for these two variables, that can be done. So what we are going to do is now, when we take output in R, especially when it comes to a graphic, the graphic is coming from in the same window. So when we call a particular graph, and then when we call another graph using another function, the first graph, it's getting disappeared. So if you want all these graphs in R, when you call a graph, like for an example, now in this case, when you call this one, when you get this graph, what you have to do is you have to save this file. So if you just right click, you can see, you can copy this, so you can save this into another email. You can save this, so you can just, when you're doing the analysis, when you're writing the interpretations, you can use that. Because when we call the next function, when we call another output, you will get the output in the same window that will overwrite on this one. So we will lose this output. So that one you have to specially remember. Now what I'm going to do is I'm going to take two graphs at the same time in the same output. So in that case, I have to take the output screen and I have to divide my output screen into two parts. So that can be done in R. So what you have to do is we can use this function par, and inside brackets, we are going to use this mf row. So what we are doing here is we are asking R to divide our output window into particular number of rows and particular number of columns. So you have to give that specific value here. So if I'm going to divide my output window only into two parts, I'm going to say I want only one row and two columns. So that is how it depends on how you like. So if you want to appear your graphs one below the other, you can say you want only two rows and one column. In this case, I'm going to I want my graphs to appear in one row, right? So that's why I used, I'm going to divide my output as in one row and two columns. So when you call this one, you will see, you will get this output window for the graphs. Now that you cannot see that they have divided the output window into two parts, but when you call the graphs, you will see that you will get both graphs in the same window. Now we'll see how to do that. So I'm going to take box plots for the two variables, speed and dist. So in that case, I'm going to use this function box plot. And within brackets, so I'm going to use the variable speed in cast data set. So what I have to do, cast $mark speed, and then I can give a name to this. If I want, I can give a name. Let's say main. This is speed, and then I can actually check. By looking at the box plot also, it's possible to check whether there are outliers. But in R, we can just check after obtaining the box plot. We can ask R to check if there are outliers. We can ask R to give that specific observation number with the output. So that can be done. So for that, we are using this function sub. So in that, you have to use paste right, sub equal paste, and here this is we are asking R to print the outlier row. So this is just for the output. Outlier rows. So when you use this sub paste outlier rows, that is under your graph, below your graph, they will, below the graph, they will just print this outlier rows and give you the observation if there are any outlier in your data set, right? And then I have to put a comma. So here I have to check. Now what I'm going to do is I'm asking us to print outlier rows below your graph, and then we have to get the number. We have to ask R to check what is the observation which consists an outlier in R. So that we can done using this right, boxplot.stats. That is the function we are using. So when we use boxplot.stat function and when we pass the argument as car speed, because that is the variable that we are interested, and again $mark out, that is the outlier we are interested. And let's see what will happen when we call this function. So I'm going to show you the graph. See, now when you look at the output, you can see in one side of our output, you can see the box plot for speed variable, and below that you have this outlier rows and you have nothing here. That means in this case for this variable speed, you have no outlier. So we can do the same thing for the next variable, that is the distance. So I'm going to just replace all these values, the variable speed by distance. So here I'm going to use this as dist, and here it should be, yeah. Now let's check the graph. Okay, so you can see now in this case, when you have both graphs in the same output and below the graphs, you have the outliers. So in the first case, you have no outliers. And when you look at the second graph, you have one observation as an outlier. So in that case, that observation is 120. So that is this 120th observation in this data set can be considered as an outlier. So I'm not going to do the remedies that we are going to apply when we have outliers. This is just to show you how to recognize outliers in your data sets, because we will be discussing how to analyze your data when you have outliers in the coming up lecture. So in this case, you should be able to understand how to obtain these graphs. Okay, so up to that point, is that clear? Any questions? So I hope after the lecture that you all are doing and you all are checking all these codes, and otherwise I don't think that learning a software is not just looking at the screen while I'm doing. So you have to practice it by yourself. So it's very important to run all these codes by yourself and say. So please take time for that and do. Otherwise, you'll never get, if you are not familiar with the software, it's hard to understand, right? So you have to again and again practice these codes, and most of the R codes are available in YouTube and in Google. So it's very easy to get familiar with R. So please do that, okay? So now we have checked, we obtained the scatter plot and we obtained the box plots. And now we can check the correlation between the two variables. So as we discussed in the earlier example also, we can use this function. And here are two variables, cars, the speed and the dist, which is coming from the cars data set. So I'm going to use cars $mark speed, comma, cars $mark dist. So we can see the correlation. Again, there is a strong positive correlation. Now in this case, without use, if you do not like to use this $marks, I taught you the other day also, we can use the function attach, and then we can attach our data set. So you can use attach, the name of the data set is cars, and then when you call these functions, you can straight away use the names of the variables. You don't have to use the $mark. Now in this case, if you are interested in obtaining the correlation, we can use speed, comma, dist. and then you will obtain the correlation. So that can be done. You can use whatever the method you like. Okay, now in this case, if you just, now we are going to fit a linear model, simple linear regression. So in this case, let's say, first you have to give a name for the simple linear regression model. So let's say this is fit2. I'm going to give the name as fit2, and it's a linear model. So here it's between dist, that is our y variable, and speed. So since we have attached our data set, we can use our variables like this and just use the names of the variables straight away into the function. Let's see, we have a message. Right, and okay, there's another message that I have to give y'all. That is, please send me your index numbers to get your attendance. Please inbox me your index numbers to get the attendance, right? Okay, and now in this case, if you just now the name that I gave to my fitted regression line is fit2. That is the linear model between dist and speed. Now, since I have attached my data set here, I'm not going to use cast $dist, cast $speed, right? So I can straight away use these names. But if you have not attached, what you can do is at this stage, when you're fitting the regression line, you can straight away use the names of the variables. And then you can put a comma and say data equal cast. Or else you can use the $mark. So whatever is easy for you. So since I have attached, I'm not going to use anything. So I'm going to call this fit2 regression model. So we will see the initial output in this case. We have the coefficient, that is beta naught hat, and we have the slope, that is beta 1 hat. So if you want to get some more details on what we have fitted, we can just type summary fit2. Here you can see the output. You will get the intercept value, the beta naught hat, beta 1 hat value, and the standard errors, t values, whether they're significant or not, the r squared values, everything. And then again, if you want to check ANOVA with this one, fit2, that can also be done. You can obtain the Anova table as well. Right, so you can get all these values when it comes to R. You can fit the regression line, and then you can obtain the outputs, and then you can obtain the Anova table. And if you're interested in doing the hypothesis testings for each and every variable, that is also possible. So the next thing is, now we fitted the regression line. So if we are interested in, if you want to fit after fitting the regression line, that the other thing that we are interested is we want to check for the residuals. We know we initially have assumptions when we fit the regression line. We want our residuals to be distributed as normal distribution with zero mean and constant variance. So that is something very important. So after fitting the regression model, we have to check whether all these assumptions are valid. So if the assumptions are valid, we have if the assumptions are valid, then we have no problem. But if the assumptions are violating, we have to use remedies for that. Okay. So in this case, now let's see after doing this one, how to obtain, how to check the assumptions, or how to do the residual analysis in R. So that is something very important. Now, in this case, if you want to do the residual analysis, if you want to just obtain the plot with residuals versus fitted values, we can use this function. Now, in this function, first what you have to do is, here you have to use the name of your regression. In my case, that is fit2. And if we use which, and if you use number 1, they will give you residuals versus fitted value plot. So I will show you this one. So a student asked me, now after dividing your screen into 2 parts, how to undo that. You don't have to undo when you just call the next output. If you are just calling that as in one window, you will again get the output as in a one window. Now see, here I just called plot. I didn't ask my, I didn't want to divide my screen into 2 parts. So I'm just calling the function plot. So you will get the output as in a one window, right? So here in this case, if you use this function plot, and if you just put your, if you just indicate the regression, fitted regression's name, and then if you just put which equal 1, so in this blue color means the color of the observations that you use to plot, then you can clearly see in this case you will get the output with residuals and fitted values. So that is your x-axis is fitted values and your y-axis is residuals. So in this case, if you are interested in checking for the normal condition, because we want the residuals to distributed as in a normal distribution with zero mean and constant variance. So there you can obtain the normal QQ plot. So for that, what you have to do is you have to just go to plot, and here you have to indicate the name of the regression model, and you have to use which equal to. So if you type which equal to, you will get the QQ plot. So I'm going to run this. So you will see here, you will get the QQ plot. Now, when we look at this QQ plot, if your residuals are normally distributed, all of these observations should nicely lie on this line. Now, in this case, we can see there are some deviations here. Here, when you go to the observation 35, 23, 49, there are some more deviations. So it seems like this is not normally distributed. So you can obtain the normal QQ plot using this function, function called which to check the normality of your residuals, and then to check whether our residuals are having a constant variance, we are using the scale location plot. So for that, the same thing we have to do. We have to just indicate the name of our fitted regression line, and here we have to use which equal 3, right? Which equal 3. And then you will get the scale location plot. So I will show you the plot here. Now, when you look at the plot, if your observations are distributed in a constant band, we can conclude that your residuals are having a constant variance. So in this case, for me, it's I can see here, if you look at the beginning, the observations are distributed in a constant band, but when the observation value is increasing, the variance is also seem to be increasing. So I think it's showing an increasing trend and with the cone shape. So for me, the residuals are not having a constant variance. So like this, we can check the assumptions of the residuals as well. You can obtain these charts using R. Okay, up to that point, you have any question? Let's see whether there are questions. Any questions, students? You understand what we discussed, like you are going to fit a regression line using a built-in data set or your own data set in R, how to do that? Is that clear? So if you have all your data sets in an Excel sheet, so that also can be done, because what you have to do is you have to in the last session we discussed how to import your data set to R. So you can just import your data set, and then what you have to do is you have to just you can just give a name to your data set, and then you can attach it, or else you can use that name with the $mark, and you can use the same codes to run a regression model. So one more thing. Now, when it comes to regression, now we discuss, if you look at our first regression model using this XY variables, which I name as fit1. This was our first regression model. Now, in this case, we actually what we did was we wanted to predict the weight of these students using their height values. So let's say we have one student with the height of 170 centimeters, and we want to predict the weight of that student using this regression model. In that case, what you have to do is first you have to store the value that you want to predict into a data frame. In this case, I will take the value that we want to predict as A. So I'm going to put the value into a data frame using data.frame function. And then the value that we want to predict is x equal 170. This is the value that we want to predict. And then I'm going to give a name for the result or the predicted value. And then we have to use the function predict. And within brackets, we have to give the name of the fitted regression model. So our fitted regression model was fit1. So I'm going to give the name as fit1. And then we have to give the data frame, which consists of the values that we want to predict. So here it's A. And now, if I call result here, okay, give me a second. I'll just run these ones, our x variable and our y And then we fitted our regression model. Let's give a new name and try. Let's say this is the regression model, relation between X and Y. And here we have a new data point. Let's say A. And then if we want to predict this, yeah, right. Now what we have to do is the same thing that, sorry, there's a small mistake that I have done here. So what you have to do is first you have to store your data, the value that you want to predict into a data frame, data.frame x equal 170. And then what you have to do is after that, I'm going to give, here we are going to use the fitted regression. The name that we gave is fit1, and we are going to give a name for this result as result predict fit1a. And then what you have to do is we can use this result, and then we can call this function result, and then we will see the output. So we call it, so we can see okay, here there's something wrong with this predict function because when it comes to the results, it cannot be 865 because we are predicting the weight. So in that case, yeah, I'll check with this and I will let you know the prediction part. So I think there's something wrong. I will double check that, and I will let you know in the next session. So up to that point, except the prediction part, do you have any questions, students? So in your exam also, I'm hoping to give you these R outputs and asking you to, I can ask questions and then you can give answers based on these R outputs. So because of that, you have to be very familiar with R. Okay, so I'm not going to give you a practical exam, but I will give you outputs and I will ask you to answer the questions by looking at the output. So you have to be very familiar. So we will do, when we can discuss sample questions after we finish our syllabus. So don't worry, but until then you can practice all these codes and yes, here, okay, very good. See, one has told me the mistake that I have done. So here the R is case sensitive, so I have just included simple X here. So I have to include capital X. So I have a data frame data frame capital X 170, and then what I have to do is I have to use the predict function, and then I'm going to predict this variable A. And then if I just call result, yeah, very good, thank you. So here you get 76.22869 as the predicted weight value. Okay, see, now when you're very good with R, you can easily identify the errors that you make. Okay, thank you for that. Okay, with that, if you have any other questions, you can raise now. Okay, so if you have no questions, I'm going to stop for today, and we'll be discussing about theories from Tuesday session onwards. And when we complete the multiple linear regression, then again we'll discuss about conducting multiple linear regression using R. Okay, then I'll stop for today. Thanks for joining with today's session and have a nice day.
Thank you.
Thank you, madam.